Charcot neuroarthropathy is a devastating complication of diabetic foot disease, which remains poorly understood, and if left untreated leads to the development of major foot deformities and subsequently ulceration and amputation. As the midfoot is commonly affected, with destruction throughout this region resulting in the classic rocker bottom foot, I wanted to investigate changes in the mechanics of the foot when these deformities occur. To do this, I created patient-specific musculoskeletal models of the foot to see how they differ from that of a healthy population. This project was carried out as part of my PhD thesis, and ethical approval for this project was granted by NHS North East Tyne-Wear South Research Ethics Committee. A lot of precautions and a strict protocol were in place due to the vulnerable nature of this patient group. Participants with diabetes and a diagnosis of midfoot Charcot neuroarthropathy confirmed by MR were recruited from 4 clinics across NHS Lanarkshire and Scotland. Participants were excluded from the study if they had any active ulceration or active skin or nail infections below the knee. Participants were also excluded if they had any comorbidity, physical impairment or disability which prevented them from walking unaided. Finally, participants were excluded from the study if they had a diagnosis of any other type of arthropathy. 6 participants were recruited with a total of 7 feet tested before COVID restrictions resulted in the suspension of recruitment and testing. Before testing occurred, the participants' feet were examined by an HCPC registered podiatrist to make sure that the patients were safe to walk barefoot. Participants underwent 3D motion capture with the marker set seen in Figure 1. Electromyography data was collected simultaneously with the motion capture data using surface electrodes. Throughout testing, the participants were restricted to how many steps they could take in order to protect the foot. They did no more than 4 walking trials, and these trials involved the participant only stepping on and off the force plate while resting in between trials. This data was used to develop a 5-segment musculoskeletal model of the foot using Visual 3D. Barefoot plantar pressure was also recorded using an EMED pedography platform with the same walking restrictions as the motion capture collection. This pressure data was analysed for selected regions of interest. Figure 2 shows some of the kinetic results for the ankle. The plantar flexion moment can be seen in Figure 2A, and this moment was smaller in the Charcot group on average by 43%. Both the Charcot group and healthy control group reached maximum plantar flexion moment around the same time of stance phase. Figure 2b shows the results of ankle power. The Charcot group reached an average ankle power of 0.8 watts per kilogram, which was 5 times less than that of the control group. This is likely a result of slow walking speed in the Charcot group. Kinematic results for the forefoot and the coordinate system of the midfoot can be seen in Figure 3. What is evident straight away is that there is variation in results across the Charcot group for all variables, which indicates altered biomechanics as a result of patient-specific deformity. Across all planes, the Charcot group had a bigger range of motion. Figure 5 shows the peak pressure and contact area results from the plantar pressure analyses. For the analyses, the foot was divided and massed into 11 regions of interest, being the lateral and medial heel, the midfoot, metatarsals 1 through 5, the hallux, the second toe, and toes 3 to 5. In Figure 5a, you can see that the Charcot group had a higher peak pressure than the control group for the total area. The largest peak pressures were present in the midfoot and were much larger than that of the control group. In some individual cases, the EMED platform was actually saturated. Therefore, the Charcot average for the midfoot is probably much higher. These large pressures match the deformities which are present in the foot, as can be seen clearly in Figure 4. The peak pressure is a direct result of the bony deformity in the midfoot. There was also increased contact area in the midfoot by 11%, while all other regions had reduced contact in the Charcot group. Figure 6 shows the results for the electromyography. The EMG signals were normalized to a fast walk, and the signals were processed using a linear envelope. The Charcot group had low normalized EMG signals across the entirety of stance phase for all muscles tested. Muscle activity was on average maintained at 0.1 to 0.2 normalized signal during weight bearing with absent phasic patterns. There was no evidence of increased muscle activity for tibialis anterior during loading or the gastrocnemius muscles during push-off. The altered muscle function is consistent with structural foot changes and reduced walking speed. Midfoot Charcot neuroarthropathy is characterized by important changes in foot biomechanics, and these biomechanics are highly variable and consistent with individual patterns of foot pathology.